So maybe that, 1 plus, so then this would be I times 2 over n. Okay, if you do it this way, then what am I kind of talking about here? What I'm talking about is that the other option is that when you looked at this Riemann sum, you thought of g as root 1 plus x. Yeah, and therefore the input to the function was I times 2 over n. Okay, it is perfectly legitimate of you to think of this function as the function root 1 plus x. And if you think of it as the function root 1 plus x, then whereas previously all this red stuff in the green circle was your input, now the input will be this I times 2 over n thing. And if that's the case, then you're going to get a different picture. You're going to get the picture of the root x plus 1 function. Well, what does the root x plus 1 function look like? It looks like, well, it's going to be root x but moved 1 to the left, and it's going to be something like that or whatever. Getting very frustrated with my lack of board space. Okay, and now what is the first thing I'm plugging into this function? Well, when I is 1, I am plugging in 2 over n. So now, contrary to before, the first number that's getting plugged in is 2 over n. And what's the second number that's getting plugged in? Well, when I is 2, then I'm plugging in 4 over n. And when I is 3, I'm plugging in 6 over n. So I'm still skipping by 2 over n each time, but now when do I stop? Well, I stop when I is n, and when I is n, in fact, I end up at 2n over n, otherwise known as 2. Okay, the point is that under this analysis, I have a different function under discussion, and also it turns out that the area that I'm trying to find here is the area between 0 and 2. Right? This is 0 and this is 2. But it's the area between 0 and 2 in the root 1 plus x function. And it's still true that I'm using RRAM, it's still true that I'm adding up n things, so it's still true that there are n subintervals. It's still true that delta x is 2 over n. And so it's still true that I have to stick in a 2 and undo the damage with a 1/2. And, but I now recognize, so to speak, that the thing that I was trying to find the area of was the area under the root 1 plus x curve from 0 to 2. And by patching up this delta x so that it's the correct width, I now see that this can be interpreted as 1/2 the integral from 0 to 2 of root 1 plus x. Okay, and how could these both be right? Well, of course they can both be right because there are many different integrals which happen to have the same value. And to convert this, and how would you actually do this integral, you might ask? Well, the way that you would do this integral is by doing a u sub. And so when you let u be x plus 1, so that du is dx, and when you convert this integral into 1/2, and now this becomes root u du, what you are really doing at the moment when you perform this substitution is, well, okay, what's u of 0? When x is 0, u is 1, and when x is 2, u is 3. And so just like that, we have seen that this process of substitution that you perform on integrals, in fact, converts this integral directly into this integral, right? This, I'll put a purple box now around the sort of answer that we got from our first attempt, and here, by substitution, I've converted that back into that. Okay, answer 3 is, I think, the most amazing thing of all. Oh man, anyone still watching this? So this is the limit as n goes to infinity of 1 over n times the sum from I equals 1 to n of, and now this is might be the way that the majority of people thought of, which is they looked at this root 1 plus 2i over n thing, and what they saw was the root 1 plus 2x function. If you looked at that and saw root 1 plus 2x, then what you were subbing were things of the form 1 plus 2, and now sort of like here was the input. The input being I over n. And this is perhaps maybe the most simple because under this interpretation, okay, what does this function even look like? Well, you need to be pretty good at function graphing to even maybe understand this. This is like square root of 2 times x plus a half. Okay, so what does that even mean? That means that this whole thing is going to be kind of pulled 1/2 to the left. So that's 1/2. Yeah, and sorry, is that even true? Yeah, and then we're gonna do whatever. Okay, so this is this function h. But what's the first thing I plug into this function? When I is 1, I'm plugging in 1 over n. So 1 over n. When I is 2, I'm plugging in 2 over n. When I is 3, I'm plugging in 3 over n. And I go all the way out to n over n. And, okay, I don't even feel like drawing these rectangles anymore, but I can. Oh man, this is one of the coolest lessons of the year, but it's so hard to do remotely. I hate you, remote learning. Okay, so what is this shape that I appear to be trying to find the area of? The shape that I appear to be trying to find the area of is this shape, from 0 to 1 of this function. In other words, the maybe simplest answer to this problem is that this limit can be interpreted, if you think of the function as the root 1 plus 2x function, then you can think of the input as just changing by 1 over n, 2 over n, 3 over n, up to n over n. In other words, the answer to this problem is just the integral from 0 to 1 of root 2x plus 1. And why this is simpler is because here, yeah, I'm using Rm, yes, I'm using n subintervals, and since since I'm only integrating from 0 to 1, then delta x just is 1 over n. And so there was no kind of correction factor like there was above. And therefore, this is maybe easier or something to get from the Riemann sum to this integral expression. Finally, I will ask once again, what would you now do if it were your job to compute this integral? Well, what you would probably do now is a u substitution. And that u substitution would be to let u be 2x plus 1, in which case du dx would be 2, and so du would be 2 dx. And so you can think of this mysterious u substitution thing that we've now been doing for weeks as a kind of just to finish the problem, that would be a 2. You'd have to stick a 2 in there. And so now it's at the moment when I go to solve the integral and I start to use techniques of integral substitution that the 1/2 kind of pops outside here. And of course, okay, big surprise, what are we going to get? We're going to get 1/2, well, maybe I'll do it in purple. We're going to get 1/2 times the integral from, well, when x is 0, u is 1, and when x is 1, u is 3 of root u du. In other words, the same answer as we got the previous 2 times. And you can actually think, I guess it depends how you want to think about it, right? This this weird like 1/2 correction thing is really just sort of U substitution happening on like the Riemann sum level. Or perhaps a better way of thinking about it is that U substitution is just a bookkeeping way of keeping track of this, sort of forcing you to have your rectangles all have the same width. Okay, good. So this is 3 sort of different ways of doing this problem. Okay. Oh my God, how long is this video? Terrible. Let's just quick finish this packet. If you understood all of that, then you just really understand what an integral is, and what substitution is, and you have just like a deep geometric understanding of everything that's going on. Last 3 problems are hopefully very short. Number 11 says kind of cryptically, without computation, which who knows what that means, show that this is true. I should probably like rewrite this question because what I think I mean is without doing the integral, show that this integral is between 2 and 6. I guess you just kind of can't do this integral, by the way, not with any techniques that you're aware of. Okay, this was meant to be sort of an exercise in integral properties, and so here's my argument. My argument is, all right, suppose x is indeed some number between 0 and 2. Well, if x is a number between 0 and 2, what can I say about x cubed? Well, x cubed must be between 0 and 8. Fact. Well, if x cubed is between 0 and 8, what can I say about x cubed plus 1? Well, it's going to be between 1 and 9. Okay, well if x cubed plus 1 is between 1 and 9, what can I say about the square root of x cubed plus 1? I'm using lots of facts about these functions such that like square root is increasing, but I hope you agree that this is legitimate, that it must be between 1 and 3. And if this function is always between 1 and 3, then I apply an integral property which says that the integral from 0 to 2 of 1 has to be less than or equal to the integral from 0 to 2 of root x cubed plus 1, which is less than or equal to the integral from 0 to 2 of 3. And this is just 2, and this is just 6. So that's what's going on there. Great. Number 12 says f is odd. Oh boy, okay. F is odd, so I need to like think about this. And we're taking the integral from 2 to 5 of f is 8, and the integral from 2 to 5. Oh, find the integral from 2 to 5. I think this is just a stupid problem. Because, yeah, it just is. This is a stupid problem because, what do we know? If this function is odd, then it means that the, so the integral from -2 to 2 of this odd function must be 0. And so the integral from 2, since the integral from -2 to 2 is going to be 0, then the integral from -2 to 5 is just going to be the integral from -2 to 2, which is 0, plus the integral from 2 to 5. So this is just also going to be 8. That's all there is to it. Okay, last problem, 13. Here we're told that f is even. Okay, and what are we doing? Okay, the integral from -2 to 2 of this function is 6. The integral from -5 to 5 of this function is 14. And what we want to know is the integral from 2 to 5 of this function. Okay, here is my solution. Hopefully this is pretty straightforward. If this function is even, then it's doing the same thing from -2 to 0 as it's doing from 0 to 2. And if that's the case, then I conclude from this that it must be the case that the integral from 0 to 2 is 3. And I conclude from this that it must be the case that the integral from 0 to 5 is 7. And if the integral from 0 to 2 is 3 and the integral from 0 to 5 is 7, then the integral from 2 to 5 must be 4. Okay. Woo! Good. We're done.